Hello everyone, and welcome to your first Show Me lesson for college algebra. We are going to be picking up right where we left off. Last class we talked a lot about quadratics and figuring out how to find the vertex of quadratics if it is in vertex form, how to find the vertex if it is in standard form, and then how to determine if that vertex is the maximum or the minimum of this graph or of the given function. So we're going to build on that a little bit today. We're also going to combine some things today. So this is a great example of what you're seeing right here in front of you. Find the x-intercepts and the max and min of each equation. And so we spent some time in the very front or first chapter finding the x-intercepts. And then last section, when we were last together in class, we figured out how to find the max and min. Okay? And so we will not be finished with this problem until we have found the x-intercepts or the solutions or the roots or the zeros. Okay? We will not be done with the problem until we find that and the max or min. Remember, the max or the min is the vertex. Oh my, I need a better stylus. Okay. So without further ado, let's go ahead and get started. So to find the x-intercepts, remember that usually involves factoring, or if it is quadratic, then we can use the quadratic formula. Okay. Bottom line, one of the things that we already discussed, and we'll kind of get into more so in this chapter, is how do we know how many x-intercepts there are? And we talked about how the highest power will tell us that. And so since my highest power here is a 2, then that means I'm going to have 2 x-intercepts or 2 solutions. So by the end of this problem, I should have 2 solutions there, and then I should have a vertex in the form of a coordinate point. Okay. I am going to just go ahead and factor this. Go ahead and pause the video, and you take a moment to factor this. That is not something that is new content. You should already know how to do that. If you prefer to do the quadratic formula, you can do that as well. But you can go ahead and pause this video and attempt to factor this as well. I will give you a freebie. Remember, when we are trying to solve by factoring, or when we are trying to solve for the x-intercepts or the solutions, remember we always replace f of x with 0. And so what we are actually doing is x squared minus 8x minus 20. And we're setting that equal to 0. So again, pause the video and attempt to factor this or do the quadratic formula. I will be working it out as well. So whether you use the quadratic formula or whether you chose to solve this by factoring, you should find that your 2 solutions or your 2 x-intercepts are going to be positive 10 and negative 2. And if you write that as a coordinate, then you will have 10, 0 and negative 2, 0. So there's half of our answer for our directions. The second part of our direction says find the max or min. From last class's lesson, we have to acknowledge that if you are asked to find a maximum or minimum, that is literally asking for the vertex. And then telling me if the vertex is a max or a min. And so what we have to do, we need to take a look at that original function that was given to us. Is it in vertex form or is it in standard form? A reminder that vertex form involves the parentheses with the h's and k's, and you can pull the vertex exactly the way it is written from the function. If it's in standard form, it's in the ax squared plus bx minus c format, the format that we would use for the quadratic formula. Okay. And looking at this function, we can tell pretty quickly that this is in standard form. And because it's in standard form, that means our vertex can be found by taking negative b divided by our 2a term. And then whatever we get there, we have to plug in to the function. Okay, so if I'm going to start out, I'm going to do negative b. Well, my b term is already negative 8. divided by 2 times the a term, which is just 1. And at that point, those double negatives that drive all of us crazy, we can make those a positive, which would then make this 8 over 2, and simplifying that down is just 4. And then the last thing that we have to do is go find the y value for our vertex, and the way that we do that is by taking the x value of the vertex. So instead of x squared minus 8x minus 20, we will do f of 4, which would be 4 squared minus 8 times 4 minus 20. And when I simplify all of that down, that would give me negative 36. Okay. And so my vertex is 4, comma, negative 36. And so the last thing we need to decide, yes, that's our vertex, but is this a maximum or is it a minimum? And again, from last class, hopefully you remember, this is a very easy way to figure this out. Look back at the original function. Is your leading term, so your x squared term, is it positive or is it negative? If it's positive, then your graph opens up just like the parent function, which means this is a minimum. If it is a negative x squared term, then that means your graph opens down, making your vertex a maximum. And based on that rule, we are looking at a minimum. And so that is what all the information we need. We've got our 2 solutions, our 2 x-intercepts, and then we've got our vertex, which is a minimum. So that is just a quick review, or not so quick, of what we did last class and in previous chapters. We are going to build on that for today's class. Our learning targets today, we're still going to be working with functions, but today we're going to be looking at the end behavior, and just like we already have introduced, how to figure out the number of solutions a polynomial has, and then actually calculating them. And we have already done both of those things, so we're not going to spend a lot of time on that. There's more practice than there is taking notes there. And then lastly, we'll write some equations using our knowledge about polynomials. Okay. The one new, like super new thing is end behavior, and that will actually be one of the easiest things we look at. I don't want you to overcomplicate that, just like we do with everything else in class. What does end behavior sound like? If you stepped out of a math class, how would you describe that? Okay. And I think, or I hope what you would say is what the ends are doing. So what are the ends or the legs of my graph doing? Basically, are they going up or are they going down? And that's the gist of it. That's what we'll be looking at for today. Okay, and there are a couple rules that go along with that, but again, if factoring is not your strength, then finding end behavior should be something that you prefer from today's lesson. Just a reminder of this function notation. This is specifically the vertex form. This is something that we looked at last class. So just want to remind you of that. Remember that the h and the k are where we get our vertex from, / our maximum or minimum. Okay. That also tells us we're either moving left or right h amount of times. Remember, that's backwards. And then we're either moving up or down k times for our transformation rule from the parent function. Here's some things that you definitely want to add into your notes. I want to take just a moment here to say you still should be taking notes. This is not a free pass. Your test will be timed. You will not just get an unlimited amount of time and an unlimited number of times to take your test. You will get timed on that. And so if you think that you can just come back to this video and watch it and then do your test, then you are sadly mistaken. That's not how it's going to work. So please, please, please take your notes and study just like you would any other time, because you're not going to have enough time to go back and look at your notes and try to figure out how to do every problem. You will not have enough time. So just a heads up, jumping off the soapbox now. For us to determine a couple things about functions, because remember, we want to find out all of the characteristics about functions that we can. One of the characteristics that we'll look at is if the function is an even function or an odd function. Okay? An even function is going to help us determine the end behavior in one way, and the odd function is going to help us determine the end behavior of that type of function. First thing we need to learn before we do anything else is even versus odd, because there are definitely going to be some questions on your test that revolve around this. Okay? So an even function, okay, whether it's a quadratic or a cubic or to the fourth power, yada yada, okay, all of this is going to depend on the highest power. And so you'll see here it's just written in function notation with a variable where n represents some number. Okay, so it could be anything. For an even function, your highest power will be an even number. So x squared, x to the fourth, x to the sixth, x to the 20th. No matter what that exponent is, if the highest exponent power is an even number, then that means you're dealing with an even function. And what that tells us is that the end behavior will always be the same. So on an x squared function, both legs will either be going up or they'll both be going down. And we know what happens, or we know how to make it go down. Okay? Because think about it. When a vertex is a maximum, your graph should be opening down, which means that leading term is negative. Okay? So for us to have an even function, okay, and you see a picture down here in the bottom left-hand corner, this is a picture of a positive even function. You have a positive x squared plus 1. Because that leading term is positive, your graph opens up, making this a minimum, but also telling you that the end behavior, because it's an even positive function, the left side goes up and the right side goes up. Okay? If you had negative x squared plus 12, your graph would look like this, where your vertex is a maximum, but because it is a negative even graph, the left and the right legs, or the left and the right sides, are both going down. And that's going to happen every single time that your highest power is even if it's not squared. If it's x to the sixth, if it's a positive x to the sixth, then your left and right side will both be going up. If it is a negative x to the sixth, then your left and your right sides will be going down. Okay. Now, comparing that to the odd functions, you should already have a pretty good idea of where we're going. When your highest power is an odd function, notice that it's greater than 1. We're not talking about fractions here. We're not talking about negative numbers. We're talking about an odd number power greater than 1. Then your ends of your function are opposite of each other. Okay, they're going to be in opposite directions. So they'll either be left side down, right side up, or left end up, right end down. And you can see a great example of that in the bottom right hand corner of your screen. This is positive x cubed minus blah 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 blah, minus x minus whatever. Honestly, that doesn't matter. You are only looking at the leading term, meaning the term with the largest power. Whatever it says will dictate the end behavior. This is a positive x cubed. Well, think about your parent function. The parent function x cubed looks just like this, where the left end goes down and the right end goes up. That is the same process. That is why you needed to learn and memorize those parent functions. This is why. Okay? Any positive odd function will have the left end down and the right end up. Okay? So positive x cubed, positive x to the 7th, x to the 5th, x to the 91st power, all of those will have some type of left end down, something like this happening in the middle, and then the right end going up. Now, if it is negative and odd, meaning like negative x cubed, then it's going to be backwards. The left end will be up, and the right end will be down. And those are just rules that you're going to have to memorize. And we'll get some practice looking at those more and more today. You have your graphing calculators, and I have no way of restricting you from using those now, so you're welcome. Happy birthday. Happy end of the semester / COVID-19 virus day. You'll be able to use your calculators, and I have no way of really stopping you. So utilize them when you're dealing with in behavior. This is just a diagram that demonstrates exactly what I was just saying. Okay, so starting with, if we're talking about in behavior, it's technically called the leading coefficient test. That's exactly what I was just saying. Look at the leading term. Is it positive or is it negative? Okay. If it is positive and it is odd, so positive x to the 9th, where your highest power is odd, then you're going to be dealing with one of two scenarios. If your leading coefficient is positive, then you're going to have in behavior like the graph on the left, where the left end is down and the right end's up. If your leading coefficient is negative, meaning negative x to the 9th or negative x cubed, negative x to the 5th, then your in behavior will swap. Okay? The left side's going to be up and the right side will be down. Okay? Now, everything in the middle here, that's coming from your table of values. So you're plugging in values, or you're finding those vertices if it's quadratic, or you're you're really just plugging in your x and y values into a table of values, or you're graphing it on your calculator and pulling those points off of your calculator to graph it. So pause this video, take some notes if you need to on this screen or from this screen, add it to your notes so you can study. Same thing with this slide as well. This is the same thing except when your highest power is even. Okay? And we've already discussed this. You might have already written it down. Pause the video so you can take some notes here if you need to. So our directions are pretty clear here. Describe the left hand and the right hand behavior of the graph. So tell me what the end behavior is. For part A, what's the left hand of your graph or the leg doing? What's the right leg doing? Same thing for part B and part C. Again, you've got your graphing calculators, so use them. I also, right now, don't have a way of restricting you from using Desmos. So all of you that maybe don't have a graphing calculator, you can pull up the graphing calculator on Desmos and use it, which I am a huge fan of. You know that. It's very easy to use, so you can use that now as well. Okay. Looking at your notes or rewinding in this video, we can figure out what the left hand and the right hand behavior are doing using those simple rules. So I'm going to split our screen here. For part A, my highest power is a 3, which makes this odd, an odd function. Its leading coefficient is negative, which means this is a negative odd function. Okay? And so a negative odd function is going to have the end behavior that looks something like this. And so the way that my expectation for how you would answer this, so if this was the word-for-word directions on your test, then what I would want for you is to type or write out left hand, swap colors here. I would want left hand up and right hand down. Okay. I don't want arrows drawn because arrows can get funky and who knows what you're actually writing there, kind of like true false. Okay. I want you to literally type out the words or write the words up or write the word down. Okay. Pause the video, see what you can do with part B and C. Again, you've got graphing calculators. There is no reason in this world that you should get these wrong on your test. Absolutely no reason, no excuse. Pause the video, see what you come up with. Okay, so you can check out your answers. Go ahead and pause the video again. If you have any questions, you can send me a remind message or you can email me about any of these 3. You can also see kind of a detailed breakdown of where those answers came from. Here's part A, B, and C. I've included the graphs as well, and obviously you can see the end behavior with these also. Okay. So same type of thing. I've got a couple of examples listed here for you. Don't let those parentheses and things freak you out. Okay. Treat it the same exact way that you would do anything else. Like for the first one, if I were to multiply all of those or FOIL all of these binomials out, multiply them together 6 times, your leading term would be x to the 6th. And that's all you need. Same thing for the second one. What would your leading term be? Well, it's going to be positive, and the highest power is a 4. So it's going to be a positive even function. On and on and on. Be careful of situations like that fourth one where it's not written in standard form. You're not pulling the first term, you're pulling the leading term, the largest term, meaning the term with the highest power. Okay. So pause this video. I'll add the answers in just a second, but I want you to have some time to practice these and work through these. And if you need to ask any questions, then you can send me a remind or email me through those as well. Alright, so here are your answers to those 5. Check them out. Remember, you can use your graphing calculator, but I am basing all of those on our end behavior rules about even and odd and positive and negative functions. So pause this, write down any questions you may have. Remember, if you're emailing me and asking me questions, then you need to make sure you include the problem. So if you want to screenshot from this video, pause it and screenshot it, and you can email me that. That would help me tremendously in figuring out what specific questions you have about what problems. Especially if I don't have my iPad with me, then I can look at it on my phone through the Remind app or through email. So if you need to do that, pause the video, take a few moments, add these to your notes. The second half of our lesson is coming from part of some stuff that we've already discussed, which was in our learning targets. I can determine the number of zeros or the number of solutions a polynomial has just by looking at it. That is this first statement here. The second thing you may not be familiar with, but again, remember, as smart as mathematicians are, we're not very creative with our titles. The second thing involves something called a turning point, and we'll address that in just a second. So these two statements are all about the real solutions of polynomial functions. Polynomial meaning they have a power of at least 2 or greater. Okay? So that first statement, we already know, whatever the highest power is, that's how many solutions it has. Now, that's at most how many real solutions it could have. There could be some imaginary solutions, there could be some real solutions. We're not really getting much into the imaginary solutions in this class, but what you need to know is if you have a polynomial function with a power of 7, then that means it has 7 solutions. Some of them may be real, some of them may be imaginary. Okay? We just have to keep in mind that regardless of whether they're real or imaginary, it's got 7 solutions. This second statement is all about turning points. Now, step out of math class. Turning points are literally points and when you turn, or in which you turn, meaning you turn direction. So if I come to a 4-way stop and I turn, I'm changing the direction that I'm traveling. Okay? So it's the same thing on a graph. The turning points on a graph are when I am increasing and then all of a sudden I hit a point and then I start decreasing. Okay? Here's a graph to kind of help you have that visual. So I'm starting down here on the left hand side and I'm increasing and increasing. All of a sudden I hit this point, and from that point I then decrease, and then I hit a second point, and then from that point I begin to increase again. So how many turning points does this graph have? It has 2. Well, if you learned your parent functions, you would know that this rough sketch of a graph is modeling some kind of x cubed function. Well, compare the highest power of x cubed to 2. What is the difference? It's a difference of 1. Well, this rule is stating that exact same thing. Okay? Remember, n represents the highest power that your graph has, or that your function has. So no matter what polynomial I give you, let's say I give you something like x to the 17th power plus 2x to the 5th minus 12. And that is our function. I have no idea what that looks like other than I can tell you the end behavior, and I can tell you how many possible solutions it has. So how many possible solutions does it have? Tell me how many total solutions it has. 17. I could have 17 real solutions, or some of them could be imaginary, but I at least know there's 17 solutions. The other thing I know is that this graph is going to change direction 16 times. And I know that because of this second statement. The number of solutions, which would be 17, minus 1, tells me the number of turning points, which is 16. So pause this video, jot that down in your notes because you're definitely going to want to know that. I'm going to ask you some questions on your next test about how many turning points your graph has. You've got a graphing calculator, that would be an extreme help as well, especially if I ask you to find the turning points. So hopefully you've been paying attention to those side conversations of how to find the turning points and to find the solutions on your graphing calculator, because that may be part of your test now, since everything is basically calculator active and everyone can at least use Desmos. That may be a part of your test now, that you've got some extra resources. I may be asking you some additional things using those resources, so just keep that in mind. Okay, another characteristics of functions that we need to learn is something called multiplicity. Now, multiplicity is kind of a hard term for us to figure out. It's not as much of common sense as in behavior or as turning points are, but it will still make sense, and I've got a graph here to show you that. So, to figure out multiplicity, okay, multiplicity is really going to come into play when we're talking about finding the solutions or the zeros of a function. Okay, so you'll notice up here first, when a function is in factored form, I can figure out very quickly what the solutions are. So right down here, this example, x minus 2 squared times 2x plus 3 times x minus 1 equals 0. Very quickly, pause the video, jot that function down, and tell me what the solutions are. And that shouldn't take you but like 10 seconds to write it down and get it, because you're going to set each factor piece equal to 0 and get your solutions. And so there would be the solutions that you get just by setting each factor equal to 0. However, I want you to look at the graph to the right. How many solutions on the x-axis do you see? There's definitely more than 3 there. There's 3, but you've got some weird behaviors happening. I also want to remind you that the number of solutions is found in your highest power. Well, when it's factored, you don't know what the highest power is. When your function is in factored form, all of your powers are kind of distributed out, but you can still figure out what your highest power is very easily by just totaling your powers. Okay, so what I mean by totaling your powers, on this first factor group, what's the highest power? Okay, a 2. In the second factor group, what's the highest power? Okay, it's not written, so we just assume it to be a 1. It's not 0, it's 1. Okay, and in that third factor group, what's your highest power? Also a 1. What's the total for that? It will be 4. So that means the highest power of this function is the 4th power. That should make sense to us, because if we look at the graph, it is a positive even function where the left hand goes up and the right hand goes up. So it has to be even, and it's not quadratic, so it's got to be an even power greater than 2. Okay, that's where we're getting the 4 from. So the first thing to write down in your notes is, if a function is in factored form, I can add up the powers to figure out what the largest exponent is. Okay, so pause the video so you can write that down. So there's another reason why that is so important. If your highest power is a 4, then doesn't that mean you should have 4 solutions for this function? The answer is yes, because we just talked about that. Okay? However, if I'm looking at these solutions, there's only 3. I have to have 4 for me to be finished here. Okay? So if the question said find all the solutions of this function, by totaling or adding up your exponents, you would know I need 4 total solutions. Right now, I only have 3. So where's the 4th one? Okay? And we're looking at the graph and we're not seeing where it hits the x-axis 4 times. Something's going on. This is when multiplicity comes into play. Multiplicity states this: when you have a function in factored form, those exponents tell you how many times a solution counts. Okay? So let me state that again. Multiplicity comes into play when you have a function that is in factored form, like right here. Multiplicity tells you if a solution counts more than once. Okay? So let me walk you through that very slowly. Back here on x minus 1, what's the power on that factor? It's just a 1. That means that this solution counts 1 time. So you would say that it has a multiplicity of 1, meaning it counts as 1 solution. X equals 1 with a multiplicity of 1. Okay. If I work backwards, 2x plus 3 is another factor group. What's the power on that factor? It is also a 1. So that means this solution counts 1 time. It has a multiplicity of 1. And then x minus 2, what's the highest power on that factor group? It is a 2. So here's when multiplicity really starts to make things a little weird, but it also makes it make sense at the same time. Okay? Because that multiplicity of 2 is there, that means that the solution x equals 2 counts twice. So x equals 2 has a multiplicity of 2, meaning that solution counts twice. So remind me, how many total solutions am I supposed to have for this function? We've got it over here boxed in that green. We're supposed to have 4 solutions. Well, I've got 1 solution here at 1. I've got a second solution of -3/2. And then I've got x equals 2 that counts twice. 2 plus 1 plus 1. That is 4 total solutions. That is the purpose of multiplicity. Okay. Now, in terms of what that looks like on a graph, you've got a graphing calculator, so you should be able to see this, but I want to draw your attention still to these 2 statements up at the top. We haven't addressed them yet, so I want to address those before we move on. Okay. Now that we understand that multiplicity tells us if a solution counts more than 1 time, we need to understand what that looks like on a graph. Okay. So if I have a multiplicity of an even number, okay, so starting down here, if I have a solution that counts 2 times, or if I have a solution that counts 4 times, or 6 times, or 8 times, on and on and on, then my graph is going to touch at that solution, but it's not going to cross through. Okay. So this is a great example for us to see. The solution x equals 2 has a multiplicity of 2. That is an even multiplicity. So that means that on the graph, my graph is going to hit x equals 2, but it's not going to cross through it. It's going to bounce off of it. And you can see that over here. Go to the graph on the right. Find where x equals 2. See how your graph hits x equals 2, but then bounces off of it. It doesn't cross through it. Okay? That's what your graph is going to look like. Now again, you've got graphing calculators, so that's going to be a huge help for you. But if you're in a bind, you're running out of time on your test, you need to know those types of things. Okay. If your multiplicity is odd, so say you had x equals, let's say x equals 5 with a multiplicity of 3, then your graph would do something like this. It would hit or intersect at x equals 5 and cross through it. So that's the difference. If your multiplicity is an odd number, it is going to hit at that x value and cross through it. If your multiplicity is even, it is going to hit that x value but bounce off of it. It's not going to cross through it. It's just going to bounce off of it. It won't cross through the x-axis. I just gave you a lot of information on this slide. I would encourage you to pause this video, rewind it, and make sure you take some really good notes here, because there's going to be a lot of logical or logistical questions asked about these things, and I want to make sure that you're really prepared for that. So pause the video, take some notes, jot down any questions you may have. We are coming to the end of our lesson, which is pretty good because this is about half of a class period, which is typically how we do things. We'll take a good bit of notes and discuss those at the beginning, and then we'll hit some practice. And the really nice thing about online is that we can get through the notes a little bit faster, and then if you want to back up and review them, you can. But then you also have a lot of time for individual or group practice at the end. And then, or if you have any questions, then you can contact me during that time as well. And it's not taking as much time as sitting in class. So it's actually a good thing, as long as you are still taking notes and asking good questions to prepare yourself well. Before there's any criticizing, I know that there is a typo here. I am not the most skilled speller, if that's even a word. Grammar's not my thing either, obviously. But that should say without a calculator. I think that you probably know that's what it's supposed to say, but my bad. But anyways, you've got 4 different functions here, and the question says complete a rough sketch of each function. So it doesn't have to be perfectly drawn. I just need a rough sketch. You are doing this without a graphing calculator, so I'm wanting you to try and practice in behavior and the vertex, if applicable, the turning points, and finding those x-intercepts or those solutions. Okay, those are the things that you need to have in terms of a rough sketch. I will write all that out just so you can see that. So here are those big key pieces of information that you'll need in order to do a rough sketch. So you'll want to find the x-intercepts or the zeros. I highly recommend factoring to get those, because remember, when you factor, you also can see if there's any multiplicities involved. So I'm going to factor each one of these as I work them out. But also, if it's quadratic, then you can find the vertex, determine the end behavior. So what is the left hand doing? What's the right hand doing? And then the number of turning points. Because although I'm not asking you for the specific location of those turning points, I still want to see where your graph turned. So they should be in the general vicinity of where the turning points are located, even though I'm not asking for a specific location. Okay, so I'm going to walk through the first one with you, and then I'm going to let you work through the other 3 on your own, and I will take any questions on those that you may have by email or through Remind if you're struggling with those. But let's tackle the first one. I had to shrink it down in size just a little bit, so we've got some space here. So let's tackle our first one. Anytime I want a rough sketch, or anytime I want an actual graph, you can't really go wrong with starting out by finding the x-intercepts or the zeros. And so by doing that first one, x squared minus 14x plus 49, I'm going to write that in factored form. Now, because it is quadratic, I could technically do the quadratic formula, okay? But I'm confident that a lot of us need some practice in factoring, and so that is what I'm going to stick with so that we can see that, okay? So I've got x squared minus 14x plus 49. Now, because I'm trying to factor it and solve by factoring, instead of f of x equals, I'm going to make it equal to 0. Because if that's equal to 0, then each of the factored pieces are also equal to 0. And I'm going to walk through this factoring step by step. I'm not going to do this very often because you learned this X amount of years ago and we reviewed it in chapter 1. So if you still don't get it, you need to back up to chapter 1 and look at your notes. You need to look up some videos online to practice factoring. Okay, so this is one of the few times that I'm going to walk through step by step and explain it. Okay? And again, remember, this is my method of factoring. If you learned a different method, feel free to use it. Just check your answers and make sure we have the same ones at the end. Okay? I like to do the AC method where I take the A term and multiply it by the C term, and I have got 49x squared, and I need factors of 49x squared that will give me negative 14x. Okay? And I'm thinking through my factors, 1x and 49x, negative 1x and negative 49x. I'm thinking through some others, and what I ultimately land on is a very specific set that will help me. There's only one set of factors that will multiply to positive 49x squared but add to negative 14x, and that's negative x and negative x. That's my set of factors that I need, and so I'm going to rewrite my function as x squared minus 7x minus 7x plus 49 equals 0. And keep in mind, all I did was take out negative 14x and replace it with its two factors that add up to negative 14x. Okay. From here, I group the front two together and I group the back two together. The front two, I'm looking at x squared minus 7x, and I want to take out the greatest common factor, which is just a 1x, leaving me x minus 7. And I'm going to do the same thing in the back, or the second parentheses group. I want to take out the greatest common factor, which in this case would be negative 7, and that leaves me with x minus 7 in parentheses. This is good because what's in parentheses is the same. When that happens, I am good to go. I can move on. So I'm going to keep what's in parentheses, but then I also can't forget what's outside of the parentheses. That I also have to hold on to, which happens to be x minus 7 as well. X minus 7 times x minus 7 equals 0. That means each piece is equal to 0. And so I have solutions of x equals 7 and x equals 7. Now tell me, are those two different solutions or are they the same solution? Hopefully you are saying that they are the same solution. I have x equals 7 twice. That is a dead giveaway that I have a solution of x equals 7 with a multiplicity of 2, meaning x equals 7 counts as two solutions. Those are the only solutions that we have right now. Go back to your original function. What is the highest power? It is a 2, which means that's the largest number of solutions I can have. Well, I have found two solutions. So as far as finding the x-intercepts or the zeros, I've done that. All I have to do now is just put it on my graph. Okay? So I have found my x-intercepts. Okay? Go ahead and pause that video if you need to rewind this or if you need to jot that down to add into your notes. Now this specific function is quadratic, which means it will have a vertex. All the others won't have one unique vertex. They'll have a bunch of different turning points. So really, the vertex is just to kind of help you out in graphing this a little bit better or sketching it. and it should just give us some extra practice finding the vertex. So if you don't want to do it, that's fine, but I expect you to be able to find the vertex of a quadratic even if you are doing a rough sketch. If you do not get that vertex graph correctly, I'm going to take off points because we specifically talked about how to find it. We have not discussed how to find the turning points, so I'm not going to hold you accountable to that. But I will hold you accountable to finding the actual vertex location. So, without further ado, that would be negative b divided by 2a. And then once I find that, plugging that in to get the y value. Pause the video and find your vertex. This is the work that you should be seeing or that you should have done in finding the vertex, and that would be at 7, 0. Now the other thing to help you get the sketch of this graph well done is that vertex a max or a min? We'll go back to your leading term. Is it positive or is it negative? It is positive, which means your graph's going to open up like the parent function. This will be a minimum. Okay. So some other information that you just found. You found the vertex of 7, 0, which is a minimum. So already you know your graph's going to take the shape of a U with a vertex that is the minimum. Pause the video. Take some notes if you need to. Okay. The next thing that we can address is the end behavior. Okay. The end behavior is, again, go back to that original term. For this one, it's x squared. Is your power even or odd? It is even, which means that your end behavior is either both up or both down. Okay. Then I want to look at the coefficient. Is it positive or negative? Well, there's nothing written there, which tells us it's a positive 1, which means it is a positive function. Okay. So when you have an even function that is positive, your end behavior will be left side up and right side or right hand up also. The last thing that we need to figure out before we do a sketch of the graph is the number of turning points. Well, the number of turning points is your highest power minus 1. And for this example, your highest power is a 2 minus 1. How many turning points are there? 1. Okay. So 1 turning point. So my graph is only going to change direction 1 time for this graph. Okay. Pause the video and see if you can come up with a sketch of this graph. This is what the graph of your first function should look like. So we have a solution at x equals 7. Remember, that's the same thing as 7, 0. And that counts as 2 solutions. So I'm only going to put it on my graph 1 time, but multiplicity rules say it's an even multiplicity. So it's a multiplicity of 2. X equals 7 with a multiplicity of 2. So I'm going to bounce off of my x-axis. I'm not going to cross through it. Okay. However, my vertex is also 7, 0. And you can see that in the picture of this graph. From there, my end behavior is left hand up and right hand up. So from that turning point, from that vertex, I'm going to draw my left hand going up, and I'm going to draw my right hand also going up. And if I needed to, you can see that I've got that 1 turning point, which is also the x-intercept, which is also the vertex. Pause this video, take some notes of whatever you need to before we move on. Just so you've got an example of something that's not quadratic, let's try the second one. I'm not going to walk through that one step by step, but I do want you to pause the video and see what you can come up with for that second one of 2x cubed minus 24x squared plus 36x. Remember, I would always start out with your x-intercepts or zeros, and since this is not quadratic, you're going to have to factor it in order to get your solutions. So pause the video, try to solve this function by factoring, and then go from there. From those solutions, find your turning points. From the function, find your end behavior, and so on and so forth. It's not quadratic, so you're not going to find a specific vertex. But you'll still have a good idea based on the solutions and the turning points of your change of direction. So pause it, see what you can come up with, and I'll add the assistance that you need in just a few moments. So your first step in factoring is always to take out a greatest common factor if possible. And you can do that here by taking out a 2x. Okay? When you do that, you'll be left with the x squared minus 12x plus 18. But if you start trying to factor that further, what you're going to find out is you're not going to get some whole numbers there. That it's going to actually prove to be fairly difficult to factor that piece. This step from the original to that second step is called factoring. But once you get to this step, x squared minus 12x plus 18 is not going to factor nicely. And so, because that is a quadratic piece, x squared minus 12x plus 18, this may be a place where you want to swap and then use quadratic formula. So you already factored, and now that you factored, you can now do quadratic formula. So I'm going to suggest that you pause the video again and then try out the quadratic formula and see what you come up with. Okay, so when you do the quadratic formula, you're going to get to these blue steps. So if I simplify what's under a radical, that becomes 72. Just for your reference, if you do not know how to simplify a radical, you might want to look that up online. That's not something I'm going to teach you. That's something that you should already know. Okay, so if you don't know how to simplify radicals, you need to be pausing this video or finishing up this lesson and then going and studying up on how to simplify radicals. Because the simplified radical version of the square root of 72 is 6 times the square root of 2. That's what's happening right here in this step. Okay? But when I work that all the way down and I simplify it, I will get 2 solutions from that quadratic. And since we're doing a rough sketch, decimals are okay here. That way we know how to plot the points. So I'm getting 2 solutions from the quadratic formula that are about 10.4 and 1.7, 1.8. But I can't forget about the 2x that I factored out at the very beginning. That's also a solution of 0. So right now I've got 3 solutions that I have found. How many total solutions or how many total zeros am I supposed to have based on the original function? I'm supposed to have 3, and I have found 3. And so my 3 roots, or my 3 zeros or 3 solutions, are x equals 0, x equals 10.24 rounded, and about 1.76. That's 3 solutions. I need 3 solutions based on the highest power. Do any of them have a multiplicity? And the answer would be no, because none of them need to count for more than one solution, because I have 3. That's how many I'm supposed to have based on the original solution. Excuse me, the original function. This function isn't quadratic, so I don't really need to find the vertex, but I do need to find the end behavior. The end behavior says, look at your leading term, which is 2x cubed. I have an odd power and a positive coefficient. Okay? And so look back in your notes, what does that end behavior look like? When you have a positive odd function, the left hand is down and the right hand is up. Okay. The last thing we need is the turning points. The turning points, I take the highest power for this function is 3, subtract 1, and I should have 2 turning points. So my sketch of my graph is going to change direction twice. Okay. Pause the video, see if you can sketch a picture of this graph. And then once you have that sketch, plug it into your graphing calculator. Plug the function into your graphing calculator and compare your sketch to your graph and see if they're similar. So again, when I say sketch, I'm not exaggerating. It doesn't have to be perfect. Mine is definitely not perfect. Okay? And I'm not asking you to tell me how high does the graph go up here or how low does it go down here. All I want to see is first those solutions, which you can see mine are in that gold color. Second, I want to see the end behavior. The left hand is down and the right hand is up. And then I want to see those turning points. And we don't know the exact location of them, but I know that there's a turning point somewhere here and somewhere there. We don't know how low it goes. We don't know its exact location, but I do know that there are 2 turning points somewhere on the graph. And that's all I want from you. Okay? Pause the video, try those bottom 2, and then we'll move on. Use your graphing calculator to check your answers. The very last thing that we'll take a look at is the reversal of what we just did. So what we just did was I gave you a function or an equation, and you had to tell me what the zeros are and go find the zeros and then graph it and on and on and on. Well, now I'm giving you the information and I want you to write the function or write the equation for me. So this first one, case in point, I want a function where the highest power is a 2, so it's going to be quadratic. Okay? And then my zeros are at -7, so my solutions are at -7. Okay? Now, there should be an immediate red flag or a cause for concern here because my graph, or sorry, my function has the highest power of 2, so how many solutions should it have? Okay. It should have 2 solutions, and yet they only gave me one at -7. What does that tell you about -7? If that's the only zero that is given to you, then that means that solution must count for both. It must count as a multiplicity of 2. And so remember, when we talked about multiplicity, everything that we had was written in factored form. And so when I ask you to write a function, write it in factored form. Okay? So for this first one, it's a function, so f of x. My solution is x equals -7. If I'm going to rewrite that in factored form, I would add 7 to both sides, and that would give me the factor group x plus 7. And we know that. If you don't know that, then you should, because we've been factoring and solving by factoring for a couple months now. Okay? Now, our last piece of info is that it's a power, or it's a degree of 2. Well, I don't see a power of 2 written in my function. My solution has to count twice. So throw a squared on that solution, and there's the function for your first problem. And if you can do one of these, you can do a million of these. Okay? So I'm going to jump to the very last one because it looks like it's the most complicated. It's not, but it looks like it is. Okay? And so I'm just going to jump to that one. I want a function with that many zeros. I didn't tell you what the power would be. All I told you was that I want a function with solutions at -4, at -2. I want a solution at x equals 0. I want another solution at x equals -2, and I want a solution at 4. Remember, I told you to write these in factored form. Okay? So for each one of these, rewrite them as a factor group. So instead of x equals -4, instead of having x equals -4, rewrite it by adding 4 to both sides. Rewrite it as x plus 4. And instead of x equals -2, rewrite it as x plus 2. X equals 0 is just x plus 0 or x minus 0. Either way, it simplifies down to just x. Okay. This next one, that can be rewritten as x plus 2. And then the last one can be rewritten as x minus 4. And remember, this is a function. You cannot leave off the f of x. If you do, you're losing points. Okay. Now, the last step that you have to do is just clean it up. Okay. So my suggestion would be to pull the x out the front, because that is how you would write it in factored form. and then go from there. I've got an x plus 2, I've got an x plus 2, I got an x plus 4, and an x minus 4. Now, is there any factor groups that repeat there? Any factor groups that repeat? You should be saying, yes, I've got x plus 2 twice. That means that solution counts twice. So my final answer here, if I'm writing the function, would be f of x equals x times, since x plus 2 is written twice, just write it as x plus 2 twice, x plus 2 squared. And then finish out x plus 4 times x minus 4. There's your final answer. Write a function using the given information. Okay. Pause the video, try the two in the middle, see what you come up with. If you've got any questions, let me know. We are right at the hour mark, so we have done great. If you have any questions, like I just said, screenshot or take pictures of your notes and email it to me or send me a remind message, and we can work through those. Stay tuned for any emails from me about if we have like a screen time face-to-face session where you can ask questions. We might use the Zoom application, or we might utilize FaceTime or Skype or something. I haven't figured that part out yet. Still working through it. But for now, whatever questions you have, you know how to get in touch with me, and we'll go from there. I hope you enjoyed your first lesson video. Let me know if you've got any questions. Have a good one. Bye-bye.